Hi everyone, welcome back to our AP Calculus series, and today we're going to go over optimization problems. Right. So we usually need to find like the maximum or minimum of a function in this type of problems. That's why it's called optimization problems. And one of the most common way to do that is to use the first derivative test. Which means, for example, you have a function f of x, and then you try to find its max and min. So first step you're going to take is to find the critical point of it, because some critical points are usually the local max and min. Therefore, you're going to derive it, which would give us f prime x. And then you're going to do first derivative test, which would be setting it to 0, or just make it does not exist. Usually we just set it to 0, doesn't matter. Alright, so let's begin to work through a few example problems. Alright, so the first one. We have a piece of cardboard that is 50 centimeter by 20 centimeter, and we're going to cut out the corners and fold up the sides to form a box. Determines the height of the box as well gives the maximum volume. Okay, so if this is space, then this would be length, and this one would be height. And if we draw base, length, and height onto this cardboard graph, then we'd have this is length, base, length, base, and the length of those little squares would be the height. Okay, now we have all the sides of the box set up. So let's just begin working through the problem. So as we know, the volume formula for a box would be B times L times H. And the B in this case would equal to 20 minus 2H. L would be 50 minus 2H, and H would just be H. Therefore, VH equals 20 minus 2H times 50 minus 2H times H. And that will give us 1000 minus 100H minus 40H plus 4H squared times H. And this will give us 4H squared cubed minus 140 H squared and plus 1000H. And the next step is to find the maximum and minimum of the function. So we use a first derivative test. So we derive v of h, and this will give us 12h squared minus 280 h plus 1000. And then we set it to 0 to find the critical points. And we would get 3h squared minus minus 70 h plus 250 equals 0. And if we use the quadratic formula to solve for h, we would get 70 plus minus 70 squared minus 12 times 250 over 6, and this will give us 35 plus minus 5 square root 19 over 3. And this is approximately 4.4 or 19. Now the last thing to do is just to plug those numbers, which are the root of the equation, back into our initial formula to see which one would be bigger. So if we plug in 19, we would get 20 minus 2 times 19, times 50 minus 38h times 90. And obviously we can see that this one is positive. However, the first term was negative, therefore the result would be negative. But the volume of the box cannot be a negative number, therefore we will know that 4.4 would be the height of the box that would maximize the volume. Right, now let's look at another problem that is related to the cost instead of just the volume. Okay, we want to build a box whose base length is 6 times the base width, and the box will enclose 20-inch cubed cubes. So the volume is 20-inch cubed. The cost of material of the side is $3 per inch square, and the cost for the top and bottom is $15 per inch square. Determines the dimension of the box that will minimize the cost. Okay, so now we want to build another box that will look like this. Let's just call the width to be W, or just call it X, doesn't matter. And so length would be 6x. And because the volume is already stated in the problem, then we can just write our equation that will look like this. 6x times x times h equals to 20. And h equals to 20 over 6 over times 2 x squared. And if we simplify this, we get 10 over 3 x squared. Okay. So now let's write out the equation for the total cost. So the total cost would be c of x, and it would look like this. 2 times 6x times 10 over 3x squared times 3 plus 2 times x times 10 over 3x squared times 3 plus the top and bottom. So the top and bottom would be 6 x squared times $15 times 2, because we have both the top and bottom. Okay, and now let's rewrite the equation. So it will look like 120 over x plus 20 over x plus 30 times 6, which would be 180 x squared. And we can rewrite that as 120 x to the power of 1 plus 20 x to the power of 1 plus 360 x. No, sorry. We're not yet to derive it, so it would be 180 times x squared. And if we derive the equation, we'll get minus 120x, actually 1 over x squared, because it's x to the power of negative 2, plus minus 1 times 20, 1 over x squared, plus 360x. And we're going to set it to 0. Alright, and the first thing we're going to do is to time both sides by x squared to cancel out the denominators. So we get negative 120 minus 20 plus 360 x cubed equals to 0. And then we will get 360x we got 360 x cubed equals 140, and x cubed would be 140 over 360 This would give us 7/18. And x would be 7/18 to the power of 1/3, which would be about 0.73. Okay, so now we already know that x equals to 0.73 centimeter, and then we can just plug it back into the h function and the length function to get the complete dimensions of the box.